Let's just wait for a couple of more minutes, see if someone else joins, and then we'll start. Let's begin. Hello, everyone. This is Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. So we'll go over the contents of week 7. Before that, we'll just look into the assignment questions of week 6 and try to solve those. Okay, so let's begin. So before that, let's just revise the few concepts that were used to solve the questions. Am I audible? Can you just confirm if I'm audible? Thank you. Right, okay. So we had started with stability concepts, stability, longitudinal static stability, and that I repeat multiple times, but it's very important that the only condition for longitudinal static stability is that Cm alpha is less than 0. This one. This is the only condition for static longitudinal stability. Another thing that we saw that we require Cm not to be greater than 0. Why? So that you can trim your aircraft at positive angles of attack. But it is in no way related to stability. It is not even a necessary condition. It is just for you to trim your aircraft at positive angles of attack, which is usually the case. The only condition for stability is Cm alpha less than 0. Then we studied some concepts regarding neutral point. Neutral point is just like the aerodynamic center for a wing. Neutral point is for the entire aircraft. It is the CG location at which Cm or the pitching moment does not change with respect to angle of attack. That means your slope, Cm alpha, is 0 at neutral point. It's the CG location where Cm alpha is 0. So at neutral point, your aircraft is neutrally stable. So if your CG is at the neutral point and you deflect your elevate aircraft, it will just attain the new equilibrium point at the new position. It will not try to come back to the original equilibrium point. It will also not go away from the equilibrium point. Okay. Stable aircraft will try to come back. Unstable aircraft will go keep deviating further, and neutrally stable aircraft will attain a new equilibrium point at the deviated location, disturbed location. So the formula for a neutral point was given by this. And we saw while doing a few questions how other components. So this only involves the wing and the tail. So if you were to add the fuselage, you just one more term would be added there. Similarly, if any other structure is added, canard or engines or fuselage, a fuselage is dealt with. Okay, so you just keep adding terms to this neutral point equation. Then we've seen static margin. Static margin is what? It is a quantitative measurement of your stability. So if your static margin is positive, your aircraft is stable. And more positive it is, more stable your aircraft is. So if it is more stable, it is more difficult to control. Okay, it's vice versa, more difficult to maneuver. Okay. So the equation for static margin is the negative of the slope of dCm upon dCl. So the slope of dCm dCl is negative. So for a stable aircraft, Cm versus Cl is negative for a stable aircraft. So because of this negative sign, you have this term to be positive for a stable aircraft. And it is equal to np minus xcg, which means that for a stable aircraft, you require your CG to be ahead of your neutral point. So it's just this term that I had mentioned, CAN. If it's just a wing, your CG should be ahead of aerodynamic center. If it's the entire aircraft, your CG should be ahead of the neutral point. It's not something that I used to remember easily. Okay. Then we moved on to controls. Control was what? It was just to trim the aircraft at different CLs. So now this CM versus CL graph you have here. If I wish to trim it at a different CL, this was your original CL trim. This is CL trim 1. This is CL trim 2. Now if I want to trim my aircraft at CL trim 2, I deflect my elevator, deflect my control surfaces. But it no way changes the slope. So you can see that even if I move the graph slightly up or down, the slope remains the same. That means dCm upon dCl is same. That means your static margin is same. So the control surfaces have no effect on the stability. And this is not just in longitudinal stability, it's in all three directions. Directional stability, lateral stability, longitudinal stability. Control surfaces have no effect on stability. It's to control the aircraft, it's to maneuver the aircraft, but it does not change the stability in any way. Okay, so it merely shifts the intercept. So here what we can see is the CM naught value is changed, but the CM versus CL slope remains the same. So stability is same. Only the CM naught value is changed. Then we saw the equation of how much you should deflect your control surface to get the required CL trim. This is that equation, right? So delta E trim is the elevator required to trim the aircraft at the given CL trim. All the other values you know, just plug it in and you know. Again, this slope, this graph has a negative slope. Okay, so this is delta E trim and this is CL. and you have a negative slope. Why? Because your x and p minus xcg is positive for a stable aircraft, and the Cm delta E, we know, we've studied, is negative. Okay, so it has a positive intercept, negative slope, just like the Cm versus Cl graph. Okay, now then we studied the hinge moment. Why does the hinge moment come into play? When you allow your elevator to float. So when there is an elevator, not just when you allow the elevator to float, when you deflect your elevator, there is a moment produced at the hinge line. Okay, so that is where hinge moment came, and we saw the linearized expression for the coefficient of hinge moment here. It depends on angle of attack at the tail, it depends on elevator deflection, and it depends on trim tab deflection. Now if you were to assume that you have no trim tab and you just set the CH to 0, which is when you allow your elevator to float freely, that is when you have no moment at the hinge line, right? Otherwise you have hinge moment. If you allow the elevator to float freely, there is no moment at the hinge line. So you can set CH to 0 to simulate the delta E float, or at what angle will the elevator float if you allow it to, like if the stick is left, if it's free. Okay, so that delta E float is given by this equation. Before that, these derivatives, CH alpha delta alpha tail, CH delta E, CH delta T, are they positive or negative? Let's start with the first one, CH alpha tail. Is it positive or negative? I'll just draw this is the tail. This is your elevator. And this is your hinge line. This is your center of pressure. So because the forces are generated at the center of pressure and your hinge point or hinge line is ahead of CP, that is why you have moments or hinge moment on the hinge line. Okay. Okay. And this is your hinge line. Okay. So now CH alpha tail. This derivative, is it positive or negative? Negative. Can you try and tell me why? So CH alpha tail is dCH by d alpha tail. Okay. So for a positive increase in angle of attack, your moment will be you try to tell me why it's negative. It is negative, you're right. Because it's about the hinge moment. Yes, CH is the hinge moment coefficient. Why is the hinge moment coefficient? Okay, let's just try to, if this is your wing, tail, and that is your elevator, this is the hinge point. Now, if there is an increase in the angle of attack at the tail, you have delta alpha tail. There will be a lift produced at the tail. Will it be positive or negative? Will there be an increase in lift or decrease in lift if I increase the angle of attack at tail? Increase in lift, exactly. So you will have one delta L here at the CP. And when this delta L acts at the hinge line, you have pitch down moment, right? So this is pitch down, which is why you have negative hinge moment, which is why this quantity is negative. You're right. Next, CH delta E. CH delta E is dCH by d delta E. Is it positive or negative? Negative, exactly. Same explanation as the previous case. So if you were to deflect your elevator down, elevator deflection down, positive or negative? Delta E down, positive or negative? Exactly. Positive. And elevator deflection up is negative. Okay. Remember this convention. Okay. So if I deflect my elevator down, it is positive deflection. Again, there is an increase in lift because your camber line is increasing. Your camber is increasing. So there's an increase in lift if I deflect my elevator down. Again, this increased lift is acting at the center of pressure of your elevator. and it produces a nose down or pitch down moment at the hinge line. So that is negative. Okay. So that is why your CH delta E is negative. Similar explanation is for the trim tab. Okay. Trim tab is just another surface added here. Okay. So similarly, when you deflect your trim tab down, or if it is deflected down, your camber increases. Camber increases, lift increases. If the lift increases, again, it produces a counterclockwise motion at the hinge line, meaning pitch down, meaning negative. So similarly, your CH delta T, which is dCH by d delta T, is also negative. Okay, all three derivatives are negative. Okay. Now, this condition we had discussed even last class. For your if your elevator is allowed to float freely and you want it to be zero, what would the condition be? There are two ways to achieve this. One is if your center of pressure is at the hinge point, then there is the forces will not produce any moment at the hinge. Okay. So if the center of pressure moves towards your hinge line, or your hinge line is moved towards center of pressure, then it will have delta E float will be zero. Correct? This will be zero. Right? Another thing was the horn balance. What was horn balance? If this is your tail surface and this outer region is your elevator. Outer region is the one that can be deflected. Okay, this entire thing. Now, shade this. The shaded area will produce the moment in one direction. Will produce counterclockwise or clockwise depending on how it's deflected. And the unshaded area would produce the reverse moment. Okay, so both the moments will cancel each other and you will have zero delta E float. Your CH delta alpha tail will be zero and hence delta E float will be zero. Okay, so these are the two ways in which you can get delta E float to be zero. One is if your hinge line is at your center of pressure. Another one is this horn balance, where you have some portion of the elevator ahead of the hinge line. Okay, you have some portion of the elevator ahead of the hinge line, which balances the moment produced by the other portion. All right. Okay. Yeah. So CH alpha, okay, it was right here. CH alpha tail, CH delta E, CH delta T, they are all less than zero if your hinge line is ahead of CP. If it was behind CP, it would just be the reverse. Okay. All right. Okay. Then we study the stick force and stick convention. So pushing the stick forward is considered positive, right? Pushing the stick forward is considered positive. If you push the stick forward, what it means is that the aircraft flies with a greater velocity. If you have to fly at a greater velocity, you need to reduce your CL. Otherwise, the trim conditions will not be maintained, right? So if you want to fly at a greater velocity, you need to reduce your CL. How do you reduce your CL? You reduce your angle of attack. Because CL, we have the very neat relation CL is CL naught plus CL alpha into alpha. Okay. So if it's at the tail, it will be the CL alpha of the tail. Okay. So to reduce the CL, you need to reduce your alpha. How do you reduce your alpha? You deflect your elevator down. Why does the alpha reduce if I deflect my elevator down? Positive deflection of elevator, this. How is this maintained? If I deflect my elevator down, how is alpha tail reducing? How is alpha tail reducing if I deflect my elevator down? If I deflect my elevator down, how is the angle of attack at the tail reducing? We just discussed this. Try and tell me. Either speak up or put it in writing. Anything is fine. If I deflect my elevator down, that is positive elevator deflection, how does it ensure less alpha tail? Is it based on CL alpha tail? Okay, let's just take CL alpha tail to be something for a cambered or a symmetric airfoil. Even if it's that, how will it affect? So your tail is usually a symmetric airfoil, okay? So just go ahead with that assumption. Imagine I'm deflecting my elevator down. What happens? What is the first thing that comes to your mind? If I deflect my elevator down, what happens? What changes happen? Produces lift. Yes. Where does it produce lift? At what point? Which will cause nose down moment. If it causes nose down moment, angle of attack at the tail will reduce. Yes. Yes. Okay. So if I deflect my elevator down, like Nikhil said, the lift is increased and it causes a nose down moment. Okay, when it causes a nose down moment, your effective angle of attack or the angle of attack at the tail will reduce because your aircraft is pitching down. Okay. Okay. So then, yeah, this is something that you need to note. Delta E required, this equation that we saw, this delta E trim, delta E required, is only governed by the stick fixed static margin. Okay, it's always governed by stick fixed static margin, never the stick free static margin. Okay, so in this equation, you have this x bar NP minus x bar CG, which is your static margin. That is the stick fixed static margin, never your stick free static margin. Okay. Okay. So, yeah. So if your delta E float, your freely floating elevator, if it's already equal to how much elevator you require to fly at a given CL trim, then the pilot need not apply any force on the stick, right? So Fs is 0, stick force is 0. Now, if the delta E float is less than the required elevator, he will pull the elevator up. When I pull the elevator up, what happens? You just told me that if I pull the elevator down, the angle of attack reduces and the aircraft will pitch down. Yeah, so if I pull the elevator up, angle of attack increases and the aircraft pitches up. Yes, lift decreases. There's a delta L downwards. Correct. And the aircraft will, angle of attack will increase. All right, okay. So similarly, next condition, okay, there is a mistake here. This should be greater. If your delta E float is greater than the required, then you need to push your elevator down. Okay. Then they've given this equation for the stick force. What is LS? Delta E is the elevator deflection. What is LS? HM is hinge moment. And what is LS? I think we discussed this even in the last session. What is LS? Either LS or delta S. Tell me one of those. Try. What is LS or delta S? Okay. So this is the stick. It's hinged about a point, and if I push or pull it, this is how. Okay, 1 second. Just a minute. So this is your stick. It's hinged about a point, and if I were to push it, right? So it is hinged about this point. Yeah. Stick force distance to elevator. The angle how much we push or pull the stick is delta S. Okay. So this length of the stick, this is LS, right? So this is LS from the hinge point to the stick, right? So that is LS. And the angle, yes, you're right, is how much this is the angle, delta S. Okay, how much we push or pull the stick. Correct. And then sir had gone to derive this expression for stick force. All right. So that is what it was. So then we have this neat linear equation for CL of the tail, CL of the tail. You have CL alpha tail. Since it's symmetric, I've taken CL not to be 0. So CL alpha tail into alpha tail plus CL delta E into delta E. Okay. Now, if it's the hands-off condition, if I let go of the stick, your elevator floats freely. So you replace delta E by delta E float, proceed with the derivation, and you see that the CL alpha tail for the stick free and stick fixed condition changes. That is the only change. Similarly, proceed with your neutral point derivation. Neutral point derivation, again, you come up with this equation, right? The difference between your stick fixed and stick free neutral point. Okay. Then replace that with your static margin equation. You get this DCM by DCL free and DCM by DCL fixed plus this term. This term is nothing but this difference, right? This is the difference. How did we come to these two equations? You just replace the XNP with the static margin. Okay, CG location is same for both of those. Only neutral point location is changing. Okay, so now stick fixed or stick free, which is more stable? I think this was one of your questions. Which is more stable? Stick fixed. Why? You're right. Stick fixed is more stable. Can you tell me why? Okay, let me just 1 minute. This is one term. This is the second term. This is the third term. Now the first, because we have more control over the aircraft. Okay, let me try to understand that. You said that stick fixed is more stable, right? Is that statement true? Yes, you said that. Next, you said more control over the aircraft. That means in the fixed case, more control. Yes. Okay. So now, initially I had told you if your aircraft is more stable, it's more difficult to control. When I said static margin, do you remember that? More the stable the aircraft is, more difficult it is to control. So this statement is wrong. Stick fixed condition is not more easy to control. And that control can never be the answer of why something is more or less stable. Okay, let's just leave control out of this and tell me why. You're right, the first statement is true. Stick fixed is more stable. Why is it more stable? Why is stick fixed more stable? Just look at this last equation and try to tell me. It's the last equation. Look at that and tell me. Okay. So for a stable aircraft, your DCM by DCL, should it be positive or negative? Negative, yes. So more negative, more stable. Keeping that in mind, you tell me, in this last equation, is the first term positive or negative? Negative. Second term? Negative. Now look at the third term. VH is positive. Efficiency is positive. CL alpha tail, CL alpha wing, both positive. 1 minus dou epsilon by dou alpha positive. This entire thing is positive. Tau, control surface effectiveness parameter, positive. Yeah, so it was varying from 0.4 to 1. Yeah. CH alpha tail, positive or negative? Negative. CH delta E, positive, negative? Negative. Right? So this entire third term, is it positive or negative? Positive. So your stick fixed case, DCM by DCL fixed is negative. And you're adding some positive term to it. So it's becoming less negative, right? So this, suppose this was -5 and this is 2. It becomes -3. Less negative, less stable, right? Less negative, less stable. So from your negative, you're adding some positive and making it less negative, right? So your stick free DCM DCL is less negative than your stick fixed DCM upon DCL. Hence, stick fixed case is more stable. Is that clear? Let's go to the next slide. So this is just a comparison. I had shown this even the last time. This is just a comparison between the stick fixed and stick free case. So your CM, pitching moment at the CG, very similar equation. Only change is that DCM upon DCL, the slope is for the fixed and the free case. Okay. So which CM would be more? This value, CM, which one would be more? Okay, let's just take some values. CM naught is, say, CM naught is positive, right? So let's just, I'm just taking some random values. It's no, so it's just take 5, okay? And let's take CL to be 10. And DCM upon DCL for fixed would be -10. And DCM upon DCL for free would be less negative, right? So it will be less negative. So it will be -5, something like that. Now just put in these values and tell me which CM will be more. Stick free, right? Because your CM, DCM upon DCL here is more negative. Okay, so stick free would be more, correct. CM naught, again, only difference here is the CL alpha at the tail, which is the CL alpha prime here, which is different for the stick free case. Okay, so this was your CL alpha prime. This entire thing is CL alpha prime. Just write that. Okay, this entire thing is CL alpha tail prime. Then DCM upon DCL, what is the difference? Again, only difference is the CL alpha tail. This is the only difference. Okay, equations are very similar, only some terms are different. Okay, so DCM upon DCL is different. CL alpha tail is different. It's mostly just CL alpha tail, even your X bar NP, X bar is just CL alpha tails. That is the CL alpha tail prime. Okay, that is the only difference. The format, the pattern of the equations is the same. Okay. Now this is the question I asked in the previous session also. To reduce the floating tendency of an elevator, hinge line has to be moved aft or forward. Let me just draw this is your tail, this is your elevator, this is your hinge point, hinge line, this is your CP. Now tell me, to reduce the floating tendency of an elevator, hinge line has to be moved aft or forward. Think about it, take a minute, think about it and tell me. Backward. Okay, can you just tell me if it's towards CP, away from CP? Towards CP, exactly. So it's aft, okay? So if you move your hinge line towards CP, the forces produced lift and drag at CP will have less effect on your hinge line, will have less hinge moment, okay? So it will reduce the floating tendency of the elevator, correct? Now let's get into week 6 questions. The hinge moment coefficient depends upon the angle of attack, elevator deflection, lift to drag ratio, trim tab deflection. The CH equation we know, we saw. Which one is it? Does it depend on angle of attack, CH? A, B, D. So it's A, B, D. Exactly, you're right. So this was the equation. It depends on angle of attack. It depends upon elevator deflection, depends upon trim tab deflection. Okay, perfect. Okay. Next question. The hinge moment characteristics of the horizontal tail of an airplane are CH alpha tail they've given, CH delta E, CH delta T. Notice how all of them are negative. Okay, they're all negative, just like we had discussed. Obtain the floating angle of elevator for alpha tail 4.8 degrees and assume delta T trim tab deflection to be 4.4 degrees. In this session, I think all the questions are solved using the same equation. So can you solve and tell me? This is the equation. Can you try and tell me? They've given you CH alpha tail, they've given you CH delta E, CH delta T. They've given you angle of attack, they've given you delta T, and they've asked you to find out delta E. How do you go about doing this? We take CH as 0, yeah, equated to 0 because they've asked you floating angle of attack. So can you quickly do this and tell me? Delta E float equals minus CH alpha tail into alpha tail minus CH delta T into delta T upon CH delta E. Delta E free, delta E float, yeah, same thing. What is the value? And they are all in per degrees and degrees, so you don't really have to convert anything. It's a direct substitution. What is the value? 5.19. Yeah. So it is 5.19 degrees. It's given here. Yes, please ask. Why is CH not considered? Okay. So it's again, usually it's a symmetric airfoil. So CH naught, even if I take variation only with alpha tail, CH naught would not exist, right? Even the entire tail is a symmetric airfoil, so the elevator is also symmetric. So it's usually CH naught is always 0. Okay. Next, if the hinge line is ahead of the center of pressure, like we've always discussed, then which of the following is true? Very straightforward. Both the derivatives will be positive or negative or reverse. You would answer this question just at the beginning of this lecture. Yeah, so I think here there's a mistake where both the options are the same. Yes, C and D, it's the same option. Both are negative. Okay. Okay. Find the value of CH delta E considering angle of attack at tail to be 2 degrees, delta E minus 2.08 degrees, CH alpha tail 0.052 per degree. Again, you can see it's all negative and your answers are also given in all negative, right? Now delta E minus 2.08, delta E is up or down? Elevator deflected up, down. Which one? Up. Okay, yeah. Can you solve this question? Again, same, it's the same formula. The same formula. Again, set it to 0. D. Yes, it's 0.005 per degree. Set it to 0. You don't have, they've not given you CH delta T. So set it to 0. You have only these two terms and you have to find out CH delta E. CH delta E is minus CH alpha tail into alpha tail by delta E. All right? Okay. Then Fs can be written as hinge moment into G. Then what is G? Just write the stick force equation and find out what is left. Which one is it? Delta, yes. Again, Ls is the length of the stick from the hinge point, and delta S is how much it's deflected, the angle at which the stick is pulled, how much the stick is pulled or pushed. Okay. Okay, yeah, this is the formula. For a conventional aircraft, which of the following statements are true? Stick force is a function of fuel air ratio. DCM by DCL free is less stable than DCM by DCL fixed. Stick force, we know this is the equation. Is the fuel air ratio there anywhere? No. So the first statement is false. A is false. B. Is B true? Only second part is true, correct. So only B is correct. Perfect. Yeah, so these are the equations. It does not depend on fuel to air ratio. And delta E fixed is a negative quantity. And this is a positive quantity, so it becomes less negative. Hence, DCM by DCL free is less negative than DCM by DCL fixed. So the fixed case is more stable. Okay. All right. Now, they've given you some data. For an airplane in a pull-up maneuver, the following expression was obtained by a student for CG location of 0.35 C. They've given you DFS by DN, the variation DFS by DN, the equation. For the airplane, the stick fixed stability margin is 0.27 and stick free stability margin is 0.23. You can see here that the stick fixed stability margin is greater than the stick free. It means the stick fixed is more stable. Okay. More stable the aircraft is, more is the stability margin. and less easy it is to control. Okay. So the first question is find the stick-free maneuver point. How do you do this? Stick fixed or stick-free? How do you do this? Okay, so they're giving you two static margins, right? If the question was find the stick fixed maneuver point, you use the first equation. Stick free, you use the second equation. Let's try doing both. XNP minus X bar CG is 0.35 and this is equal to 0.27. So how much is X bar NP? How much is this value? How much is the stick fixed neutral point? 60. Now similarly, do it for stick free case. X bar NP prime is minus 0.35 equals 0.23. So your X bar NP prime is 0.58. Yes, thank you. Now they've asked you for the stick-free maneuver point. What is the condition for maneuver point? How is it defined? DFS by DN equal to 0. Yes. If it was okay, let me just stick fixed maneuver point, stick-free maneuver point. Now for this, you told me that DFS by DN equal to 0. CG location at which DFS by DN is 0. What about this stick fixed maneuver point? What is the condition? Is it the same? We had, so I think the last lecture was where last week was where we derived the equation for Fs. Prior to that, we did not have any stick force component, right? But we were still finding out the maneuver point. How are we doing that? Week 6, we derived the equation for stick force. But even before week 6, we were finding out the maneuver point, stick fixed maneuver point. How are we doing that? Okay. Do you remember d delta E dn equal to 0? I think this was one of your assignment questions from week 5, if I'm not wrong. Week 5 or week 4? It's d delta E by dn, right? This is how maneuver point was defined until you came up with the stick-free case. Stick-free case, dfs by dn equal to 0. CG location at which dfs by dn equal to 0. Okay, let's go ahead and do this. Set this to be 0. dfs by dn equal to 0. So you have 130. DCM upon DCL, what? The first, yes. So if there is no, okay, my bad. This should have been prime. Yes, I made a mistake there. The first is fixed, next is stick free. Yes. Okay. Yeah. So let's do this question. Stick free maneuver point. Yeah. So set this to 0. Find it. 130 into DCM upon DCL free. What is DCM upon DCL free? What else can you write over there? What term instead of this? The static margin in the free case is X bar NP free minus X bar CG. And this is equal to minus static margin, correct? So you have X bar CG minus X bar NP prime minus 13 equal to 0. X bar NP prime we found out to be 0.58. Substitute the values. What is X bar CG? So it's 0.58 plus 13 by 130, 0.68. Correct? So the CG location at which your DFS by DN equal to 0 is your stick free maneuver point. Yes? So your answer is 0.68. Okay? Is that clear? Okay, I'm just going to proceed. Yeah. Next question with the same data. Find the CG limits permitted if the magnitude of stick from force per G is to remain within 10 and 30. So they haven't told you if this 10 is positive or negative. Right? You can either push or pull. Push is positive. Push is the FS positive or negative? Positive or negative? This question? Okay, let's just do it again. Let's erase this entire thing. We'll do it again. Okay. So first what we did, we used this equation. They've asked you for the stick free case. Okay. So I write that down. X bar NP prime minus X bar CG, they've given you as 0.35. 0.35 equal to static margin for the free case is 0.23. Right? And so this you rightly said, X bar NP prime is 0.58. Till here it's clear? Okay. Then we use the condition. So they've asked you stick free maneuver point. So this X maneuver point prime is nothing but, in this question, the notation is different. Okay. So these are the same thing. You understand that? Maneuver point notation in the question is NM prime. We are using XMP prime. It's the same thing. Okay. So how do we find out this? It is the CG location at which DFS by DN equal to 0. Correct? You said this yourself, right? Yes. So DFS by DN, we have the equation. Set it to 0, find the CG location. So 130 into X bar CG minus X bar NP prime for the free case minus 13 equal to 0. Then you have 130 X bar CG minus 0.58 equal to 13. X bar CG is 13 by 130 plus 0.58, which is 0.68. The CG location at which DFS by DN is 0 is your maneuver point, stick-free maneuver point. Yes? Okay. So you're I don't think I was audible. Can you hear me now? Okay, yeah. So the stick force, if I push the stick, is it positive or negative? Positive, exactly. So here they've just told you the magnitudes, okay, 10 or 30 Newton. They have not told you if it's positive or negative. So you need to check the complete range. starting from minus 30 to plus 30. Okay. So plug in each value. We don't know if it's the positive or the negative limit that they've given you. So start from minus 30, use minus 30, minus 10, 10, plus 30. Okay, we'll use all four values, and whichever matches the option, we use that. Okay, so DFS by DN, let's start with minus 10, minus 30. Minus 30 is 130 into X bar CG minus X bar NP prime was 0.58 minus 13. So 1 second. So in this case, what is your X bar CG? What is X bar CG? Let's do the calculation again. I believe it is 0.4492, and CG cannot. Okay, yes. Let's try this again. 0.4492 is what I get. Yes. Now let's try minus 10. (130) X bar CG minus 0.58 minus 30. What is X bar CG here? .603, yes. Now let's try 10. 130 X bar CG minus 0.58 minus 13. What is X bar CG? 0.756. Similarly, try it for 30. So the now extreme CG limits are 0.4492 and 0.91. It cannot go beyond these two. Now just check that which of your options are matching these values, and it is 0.4492. Hence, that is the correct option. Okay, but since they have not given you the stick force limits sign, the sign values are not given if it's positive or negative, you have to try with every possible combination. Okay, don't just try one of them. It's not 10 or 30 or minus 10 or minus 30. Try all four, see which one matches your options. All right. Okay. Another question: a hinge moment coefficient depends upon. We've done this multiple times. A, exactly. So this is the equation. It has angle of attack, elevated deflection, trim tab deflection, A. Okay. Now here's a question. I think we have done something similar before, but let's just do this for, practice. For an aircraft, the tail area is 1/4 of the wing area, and the distance between the two aerodynamic centers is equal to 1/4 of the wingspan. And the wing and tail are in rectangular shape. In addition, the following data is applicable. So they've given you weight of the aircraft, cruise velocity, CL alpha of the wing, CL alpha of the tail, both are in per degrees. Angle of attack at zero lift, the mean aerodynamic chord, the wingspan, CMAC of the wing, tail efficiency factor, CMAC of the tail, distance between XCG and XAC, X bar CG against X bar AC, wing setting angle, tail setting angle, and control surface effectiveness parameter. Okay. Now let's look at the questions. First question is, the pitching moment coefficient at 0-degree angle of attack of the aircraft will be. So the pitching moment coefficient will come from both wing and tail. Okay. So try doing this. Take a moment. It will be sum of both the quantities, okay, of the wing and the tail. Pitching moment coefficient at 0-degree angle of attack is Cm naught, and Cm naught will be Cm naught wing plus Cm naught tail. So first find out wing, then find out tail. Yes. So how do you do that? Take some time, try doing it. Then we can do it together. First, you find out Cm naught wing. What is the formula for Cm naught wing? This is one of the first things that we had discussed first 2-3 weeks. And let me give you the formula for Cm naught. Yeah, Cm naught of the wing. This is the formula. Try finding it. So Cm AC of the wing is given directly to you, right? Yes. Cm AC of the wing is minus 0.009. CL naught. How do you find out CL naught? How do you find out CL naught? So for that, you need your CL versus alpha. And they've given you angle of attack at 0 lift to be minus 2 degrees. So it is not a symmetric airfoil. It's a cambered airfoil. They've also given you CL alpha. Okay, yeah. So they have given you angle of attack at 0 lift. So it's not a cambered, it's not a symmetric airfoil, it's a cambered airfoil. This is minus 2 degrees. And this is your CL naught. How do you find out CL naught? CL naught equal to how do you find out CL naught? From this graph. So you just need the magnitude. So it's just 2 into Cl alpha. It's just that change. So it's basically 0 minus 2 into Cl alpha. That's how you do it, right? So it's just 2 into Cl alpha of the wing. That is 2 into 0.09, which is 0.18. So plug that in here, 0.18. X bar CG minus X bar AC, they've given you in the question. It's 0.31, 0.031. How much is this value? Just do it. So it's 0.00342. Okay, just a minute. Zero point zero zero three four two. All right. Okay. Next, you need to find out Cm naught of the tail. Do you remember what the formula was for Cm naught tail? Let me just bring that in. So this is the formula for Cm naught tail. How do we go about doing this? So that you need to find out VH. Correct? How do you find out VH? This was the formula for VH. So let's find out VH first. How do we do this? What is ST upon S? Yes, 1 by 4. And X bar AC tail minus X bar CG upon C bar. How much is this? 1 by 4, exactly. 1 by 4. And is something missing? Yes, C bar, C bar. 1 by C bar, which is C bar? Yes, 1.2. So what is this value? It's equal to 1/4 of the wingspan. There is a B here, right? There's also a B there. It's equal to 1/4 of the wingspan. Okay, so it's 1 by 4 B into 1 by 1.2. B is given as, how do you find out B? B is not given to you. How do you find out B? Is B given to you? Yes, B is there. Okay, my bad. B is 10.5. So it's 10.5 by 4 into 4 into 1.2. How much is this value? Point 5468. Correct me if I'm wrong anywhere, all right? So now you have VH. Plug that in here. So it is 0.5468. Cl alpha of the tail. It's given to you. 0.059. Cl alpha of the tail. Eta. Eta is 0.89. Let me write that in sequence. 0.89, 0.059, wing setting angle 1.3, epsilon naught. How do you find out epsilon naught? Tail setting angle you have, right? It's already given in the question. How do you find out epsilon naught? What is epsilon naught? What is epsilon? So epsilon is epsilon naught plus b epsilon by b alpha into alpha. What is this epsilon? Downwash angle. What is downwash? Due to pressure difference of the air above and below the wing. So because of the pressure difference above and below the wing, you have lift. Yeah. So when they meet at the tip, you have vortices generated. And when this flow moves downwards, the angle of attack at the tail changes. Angle of attack and velocity at the tail changes. This is known as downwash. Okay. Okay. How do you find out epsilon naught? Now we require epsilon naught for this question. How do you find out? This was the formula for epsilon naught. Can you try finding it? Find it out and tell me how much it is. Note that since we have the wing setting and tail setting angle in degrees, and your CL alpha tail is in per degrees, you would require epsilon naught also to come out in degrees. Try, let me know when you find out epsilon naught. You have CL naught, you have pi, take E to be 1, they've given you rectangular wing. How do you find out aspect ratio? Aspect ratio, just a minute. What is the formula for aspect ratio? B square by S. And it's a rectangular wing, so you have B square by B into C, so you have square B by C. Now find out epsilon naught. It's just 2 into 0.18 by pi. E A R is B by C. B is 10.5 and C is 1.2. How much is this? Let's try doing it once. Okay. So what is the unit? Zero point 0.013. What is the unit? What is epsilon? What is epsilon naught? Is it degrees? So if otherwise, if I wanted it in radians, what I do? Is it degrees? Does this formula give you the value in degrees? I had mentioned this multiple times in the first 2-3 weeks that this formula will give you the value in radians only. Yes, so this is radians, correct? This formula, and please remember the other formula, the d epsilon by d alpha is 2cl alpha by pi e ar. It was not this, it was not, okay, just a minute. It was cl alpha by 1 plus cl alpha into pi EAR. It was this. Both these formula give you the value in radians and per radians, and the values used are also in per radians. Okay. So these two formulas deal only with radians. So this epsilon naught of 0.013 that you've gotten is in radians, but we require degrees. Converted to degrees, how much is it? Please don't forget this, okay? These two formulae are completely in radians. Radian per radian, everything. Just multiply 57.3. What is the value? 0.75. Okay. Plug that in here. So you have 0.75 minus tail setting angle. So you have 1.3. So how much is CM naught tail? How much is CM naught tail? How much is CM naught tail? I'll try doing it. It's a simple calculation. 0.961. Okay. 0.0961. So what was the question? What is the final answer? What was CM naught of the wing? Just add those two, right? How much are you getting? 0.0961 plus 0.0035 is 0.996. Okay, so none of the options seem to match here. But what is the closest? I think this is the closest, right? You take the closest. One assumption that we've made here is that we've taken this distance between two aerodynamic centers equal to 1/4 of the wingspan. But our value was not distance between two aerodynamic centers, it is between XAC tail and XCG. One assumption that we have made, we could have actually found out the proper distance because you have this value and you have the distance between the two aerodynamic centers. So you could have gotten a perfect value. One assumption that. So this is the closest. So here you can see your CM naught value you've gotten positive. Both the cases it's positive. And that is another reason why it's, yeah, I'm not very sure why. Did we make a mistake anywhere? Not really. So it's just that assumption that we made. So the closest option is 0.096. Let's just go with that. Okay. Okay. Next, the pitch stability derivative, Cm delta E of the aircraft in radians. So they've asked, yeah, previous question. Please remember that this equation will always give you value in radians. Okay. Okay. The pitch stability derivative of the aircraft in radian will be, how do you go about doing this? There's a direct formula for pitch stability derivative. Try to recall that. Just try to recall or go through your notes or whatever. There's a direct formula for Cm delta E. Were you able to find the formula or recall the formula? Pitch stability derivative Cm delta E, direct formula. Perfect. That is the formula. So you can just plug in the values and tell me the answer. So you have minus eta is 0.89. VH we've found out to be 0.5. in per radians. Okay. Into tau is 0.4. Tell me the answer. D is the answer. Correct. Your Cm delta E, again, you see it's negative. Okay. Then the trim lift coefficient of the aircraft at sea level will be. This should be simple. Yeah, 0.6592 was the whatever. Trim lift coefficient of the aircraft. How do you find this? Very simple, no? We've done this multiple times. Use the trim equation for lift equal to weight equation and try to find out. This is the formula, right? And then you use lift equal to weight and try to find out what is the value, trim lift coefficient. What is rho value, you tell me? Try to tell me. Read the question carefully again. Why is that a question? You tell me. Don't ask me. Tell me. Okay, why is it 1.225? At what are the conditions for it to be 1.225? Why did you tell it's 1.225? Is the temperature given to you anywhere? 1.225 is at sea level, right? The question says sea level. We have taken this value almost in every question. You shouldn't be asking this question now, right? 1.225 sea level. Okay. Density at sea level 1.225. All right. Okay. Now tell me what is CL trim. Now it's simple, right? Very simple. Just plug in the values. So CL trim is 2W by rho V square S. V, they've given you V cruise. Plug it in. 2 into, what is the weight? 850 into 9.81. 1.225. V cruise is 45. What is S? How do you find out S? V by C, yes. V is 10.5. C is 1.2. All right. So what is the value? Why was it taking so much time? Just plug in the values. you sure? Where are we going wrong? Where are we going wrong? How will you consider tail as well? You mean CL of the tail? No, no. This is how we do it. No. Okay. What is the area? That's where we made the mistake. What is the area? What is S? How was it 8.75? Why is it 10.5 by 1.2? Why is it B by C? B square by S is the aspect ratio, right? What is S? Yes, so that is the mistake. It's into 1.2. Now tell me the answer. Five, 3, 3, 5. That is this, okay? So I also made a mistake. You also made a mistake. Don't make this mistake again. It was a very silly mistake. We shouldn't have done this. So we confused it with the aspect ratio. It's B square by S, but the S is what we need to be using here. S is they've given you a rectangular wing, so it's just span into chord, B into C. The mistake that we made was we took B by C, okay? All right, okay. Next question. For an airplane, they've given you W by S, 400 Newton per meter square, flying at some altitude where density is 0.8 kg per meter cube. The following data were recorded. They've given you velocity readings. They've given you this push-pull is the stick force, okay? So this is the stick force, Fs. And pull is positive. Okay, here they're giving the notation such that pull is positive. Okay, it's usually the other, but if it's not specified, you take push to be positive, okay? Pull is positive. And they've given you the stick force, the different CG. Then they've asked you to find out the stick-free neutral point. How do you go about doing this? Okay, let's just discuss the 4 conditions first. Neutral point is the CG location where, what is the condition for neutral point? One condition we saw is where DCM by DCL is 0, correct? But if you were to do this while taking experiments, what is the other condition? Neutral point is the CG location where d delta E by DCL is 0, correct? Please do correct me if I'm going wrong, okay? Is this correct? Okay, let me just proceed. Now, if I were to do stick-free neutral point, we discussed this in the previous question. It is the CG location where what is the condition for stick-free neutral point? For stick fixed, it was d delta E upon dCl. For stick free, it is dFs by Q by dCl. Correct? Now maneuver point, stick fixed maneuver point. CG location where? What is zero at stick fixed maneuver point? Just the previous, I think, couple of questions before we discuss this. D delta E upon dN is zero. Last one, stick free maneuver point. CG location where? Okay. dFs by dN equal to zero. Okay, here they've asked you stick free neutral point, right? Which is this condition. This is the one. This is where what we have to use. dFs by Q by dCl equal to zero. So how do you go about doing this? Take a moment, read the question, see what data is given to you, and tell me how to proceed. You need to find out dFs by Q by dCl, the point where that slope goes to zero. That is where you find your neutral point, stick-free neutral point. So how do you start? What all data are given to you? They've given you W by S, okay, wing loading. They've given you density. They've given you 3 velocity readings. And at these 3 velocity readings, they've given you how much stick force is required at 2 different CG conditions, right? How do we proceed? First we find Q. Okay, so let me just make another column Q. All right. Okay. What is Q? Q is half rho V square. Okay. Tell me the first one. 1 by 2 into 0.8 into 50 into 50. 1000. Correct? Second case. Okay. 31313. All right. Next is 2000. Okay, just take it to be 2000. All right. Okay, then how do we proceed next? What do we do? Suppose this is Fs for first condition, this is Fs for second condition. Pull is positive, so therefore push is negative. How do we proceed? What do we do next? What do we do next? CL value. All right, let's find out CL add. Add another column. CL is you can just do W upon S by Q. Now that you've already found out Q, you can just do W upon S by Q. W upon S is 400, so 400 by Q. 400 by Q, 400 by 1000, 0.4, 400 by 2000, 0.2. What's the second one? Getting 0.3046. Okay, now what do we do? What do we do next? What do we do next? How do we proceed? What do we do next? Yeah, how do you find that out? How do we find that out? All right, so just make it and tell me what is the final answer. And then I will tell you how I intend to do it. I'm not sure what equations you mean. Try to tell me or write it down or something. How do you plan to proceed? I'm not sure what you mean by we can make equations. Try to think about it. Till now, I think it's going pretty well. We found out Q, we found out CL. Now what do we have to do? You said you have to find out DFS by Q by DCL. Okay, so you need to find out the slope. For the slope, we need 2 points. 2 points of what? So your graph should be Fs by Q and Cl. And then you should have some sort of a line. So you need 2 points for that. Right? So what are those 2 points? Fs? Do we have Fs? What is this 2 pull, 4 push? What is all this? What is this value? In the question, they've given you 2 pull, 0, 4 push. What is all that? Delta S. What is delta S? Okay, no, that is Fs. Okay, all of this is Fs. This 2 pull, 2, 1 pull, and all of that. No. This is Fs. Okay. Okay. So I've written it here. I think my audio was cut off. I'm not sure if you heard it. So this is the Fs1 for the first CG condition. This is Fs2 for the second CG condition. All right. So now tell me how to proceed. You were going correctly till now. You told me the right steps. Now what? Think about it. You need this graph. You need this Fs by Q versus Cl. So for that, you need 2 points. You have Cl. Do we have Fs by Q? Find out Fs by Q. So make another 2 columns. Yeah, exactly. So for that, you take. Correct. You're going perfectly. This is correct. So Fs1 by Q, Fs2 by Q, right? Can we just find out the values? What you said is absolutely right. Plot 3 values and then you can find the slope. Okay, so Fs1 by Q, pull is positive. So it's 0.002. And this would be minus 0.002. Right? Yes. This would be 0. This would be 0. This would be 0.001. And this would be minus 0.001. So now you got your 2 lines. Right? So find out the slope of the 2 lines. So dFs1 by Q by dCl. What is the first one? Slope of this first line. Just take the first and last point for simplicity. So the slope is 0.002 minus of minus 0.002 by dCl is 0.4 minus 0.2. This gives you 0.02. Similarly, dFs2 by Q by dCl. How much is it? 0.01, right? 0.01. Correct? Yes. So now how do you find out? You have the 2 slopes. Now how do you find out the point at which the slope becomes 0? So now you take another graph where you have dFs by Q by DCL, and you have CG. Quite clearly. The first graph that we drew was Fs by Q versus Cl. Now we need to draw another graph, that is dFs by Q by dCl, and this is Cg, right? Now plot the two values. The first one is 0.02 for a Cg location of 0.2. So somewhere here. Next is 0.01 for a Cg location of 0.25. So this is 0.2, 0.25. And then you extrapolate this. This is your stick-free neutral point. How do you find that? How do you find this point, coordinates of this point? Equation of the line, yeah. So tell me the value. What is the XCG? Yes, you're right. You're absolutely right. Consider it as 0. That is, the y-axis would be 0. Find the x-axis. What is the value? Take the coordinates of that point as x comma y and then just do it. So y is 0, right? So you have, actually, you tell me. I'm not going to do this. Just tell me. X2 minus x1 by y2 minus y1, that equation. Okay, what is the value? What is the neutral point? You have 2 points of an equation. You can't find the third point. There are different ways to define a line, right? So one is y is equal to mx plus c. Y equals mx plus c. Another way is y2 minus y1 by x2 minus x1 equals y3 minus y minus y1 by x minus x1. Do you know this equation? Can you find out now? We're done with our time. So find this out and we'll discuss this question again in the next class. So just find this out. Yes, it's 0.3. Correct, it's 0.3. So you can just directly put down the points in this equation and find out. Don't need to find the slope and all of that. Just plug it in directly. It is 0.3. I think we'll discuss this question again next class. Just go over it briefly. Yeah, please ask me. Okay. If they are a large formula, yes, you can expect the formula to be mentioned in the exam. But the simple ones that we can remember. Okay. Any other questions? Okay. If not, then we'll end the class today. We'll meet again next Tuesday. All the very best for your exam tomorrow, for your assignment tomorrow. We'll meet again next Tuesday. Thank you.